Shalom, Hello everyone, my name is In this series of video, I'm going to implement transformer with you. It contains a lot of components such as self-attention and multi-head attention. And now in this video, I'm going to implement positional embedding, which was proposed in the original paper. As you can see in the self-attention that I implemented in the last video, it has nothing to do with its position. So, for example, if you change the sequence of the input, the output, they just change the sequence, right? So the before here is exactly the same as before here. But actually, for example, in human language, sequence does matter, right? Lions eat zebras, and zebras eat lions. It might sound ridiculous, but so it's two different sentences. So we want to add positional embedding. So the PE1 and PE2 is different. So if we change the sequence, if we change A1 here, A1 added with PE2 is different with A1 added to PE1. So if you put A1 in different position, its embedding is different. That's an intuition of positional embedding. And now we are going to implement it. Right, yeah, this. Before we started, I want to show you how to generate a matrix using a row vector and a column vector, because that's the main difficulty in the code of positional embedding. So the input the row vector shape is 1 3. The column vector shape is 3 1, and the output is 3 3. You can do it with torch. So row. Now the shape of it is it's one-dimensional, right? But we want to add a dimensional before it, so we need to use unsqueeze. 0 means we add a dimension before it, so it came from 3 to 1 3. I mean the shape. For example, if the shape of it is XYZ and you use unsqueeze 0, the output shape become 1 XYZ. And if you change it to 1, the output shape becomes X1 YZ. Right? I think it's not difficult, so we are going to add sin 0 here. So the shape become 3 to 1 3. So it becomes a row vector. Now, maybe you can guess that the parameter we send to unsqueeze is 1. So and the shape comes from 3 to 3 1. Now, actually, we can although the two tensor is of different shapes, you can multiply them. I think column should come first. Yes, that's the output matrix. After doing this, I want to say why. The reason why I did this because in the code of positional embedding, the row vector is 1, 2, 3, 4, 5, and the index of the row and the row vector. They come. You can see in the formula here, and you can see the formula here. The pose is for example, it's x y, the coordinate of x y, and when you come to calculate the positional embedding, which is a number, you send x here. That's the index of row, right? And that's 2i means the index of column. So you send x y in, and you generate a number, and that is going to yeah. Let me show you how to do this. Number A means how many embedding we send in. That's the number of embedding, and the DA means the length of each embedding. The notation is same as the last video. For example, if we have 4 words, the number A is 4, and each embedding is, for example, consists of 32 numbers, so it is 32. So first we need to generate a blank matrix. Use zeros. We can show the shape of PE, and I want you to know that print is the easiest way to debug your code. Right? And we want to use torch.arange because that's a pose, right? That's a pose in the actually the pose is the index of row. So and this is the index of column. For example, if an element is in the x row and in the y column, and you just need to if the column is even and the result is x y, and these are the output. Yeah, I think I talked too much about the theory. The default data type of a range is int, so we need to change it to torch.float32. And we use unsqueeze 0 to change it to a row vector, right? And we also use a range to make it to we can see in the formula here, you need to use the index uh, the index of column to divide it by D model. So we need to divide dA here. And let me think that's, yes, I think that's it. Now we're going to talk about the indexing. What it means? It means all the element in the first dimension. So it means it starts from 0 and stride a 2. So it means all the the row 0, row 2, row 4, and of the I'm sorry, it means the column, right? And it means all the rows. So it's column 0, column 2, and column 4. What is V? Actually, V is what is in the bracket. So we calculate it. Um, if the index of column is even, we use sine, and if it's odd, we use cosine. That's in the original paper. So I'm not going to change it. Yes, that's all. Now we're going to try it. For example, we have 30 embeddings. We have 30 embeddings, and each embedding is of the dimension of 64. That's the length of each embedding vector. And number embedding. Yeah, let's see the output. Something goes wrong here. The side of a tensor must match the side of tensor B. Uh, Let me think of it. So I think I made the unsqueeze. We didn't change it to a row vector, right? I think the first should be the the column vector. So it's 1. I think it's 0. Right, and the thing before it before this character it's a row it's a column vector, and after it it's a row vector. So the column vector came first. Yeah, I think that's all. Because the shape is 30. So we have 30 embeddings, and this is dA is the shape of embedding. That's a zeros. This is all zeros, right? And we use sine for the odd column, and cosine for the no, sine for the even columns, right? And let me show you the heat map. Yeah, that's a heat map generated by this code, and you can see that here uh, the frequency. So the number of column index controls the frequency. So when you go righter, they changed, they become more stable. Yeah, I think that's all about positional embedding. Thanks for watching my video, and in the next video I'm going to implement multi-hand attention. Thank you for watching.